So we've seen that a linear equation in two variables describes a relationship between two values, x and y. For example, the equation 4x minus y equals 8 works for the xy pair 2, 0, for the xy pair 3, 4, for the xy pair 1, negative 4, also for some unpleasant pairs like 1/6, 16/3. You can check this last one with a calculator if you'd like. There are lots and lots of xy pairs that satisfy this equation. But typically when I ask a question, I'm looking for a unique answer. I'm looking for just one correct answer. In order to narrow it down to just a single point on this line, we need another equation, another condition. We might, for example, also consider y equals x minus 2, which we can also graph. And there's something that we notice. We notice that there's just one point where these lines cross. This point, x equals 2, y equals 0, is a solution to this first equation and also to this second equation. Second equation also has a bunch of solutions. 2, 0, 1, negative 1, 4, 3, 0, 2, and so on. Right. But there's only one of them, this one, that is a solution to both. When we're looking for the common solution to more than one equation, we call it the solution to a system of equations. This is what we write. We say that the point 2, 0 is the solution to the system of equations 4x minus y equals 8 and y equals x minus 2. We use this curved bracket to say that these two equations come as a group. It tells us that the equations form a special thing called a system. Just so that we've said formally what we mean by that term, a system of equations is a list of two or more equations where we want to find a common solution, that is, a single point that is a solution to both equations. How do we know when we have something like that? When we have something like that, it works in both equations. So just for example, let's consider this system of two equations. 5x minus 3y equals 5 and y equals x plus 1. Now I've labeled the equations A and B just so we can refer to them easily. Clicking in to A, we see that 5 times 1 minus 3 times 0 does equal 5. So this is a solution to A. However, 0 is not equal to 1 plus 1. So this is not a solution to the system. Similarly, 4 does equal 3 plus 1, but 5 times 3 minus 3 times 4, that's 15 minus 12 is 3, which isn't 5. So this point is not a solution to the first equation. This last point, though, 5 times 4 minus 3 times 5, that's 20 minus 15. That does equal 5. And 5 does equal 4 plus 1. Since this point is a solution to both equations, this is a solution to the system. In fact, this is the only solution to the system. Why do I say that this is the only solution to the system? Well, again, here's the graphs of these two equations. The top line is B, the lower line is A. Notice, by the way, that we can't quite see where they cross. It's going to be up here, a little bit above the top of the graph. But these are two straight lines. right? And when we have two straight lines, there are only three possibilities. Either they intersect at exactly one point, which is the typical thing for two lines to do, or they never intersect, that is, they're parallel, or maybe they're actually the same line in disguise. This first circumstance where they intersect at one point, this is the thing that typically happens. If we were to write down a system of equations at random, the lines they describe would intersect at one point. So this is what we're going to focus on. When the lines intersect at one point, when they do this normal thing, the system is called consistent and independent. Consistent means it's possible for both equations to be true at the same time. And independent means that if we know that one is true, it doesn't tell us whether or not the other one is true. We'll talk some more about this term later on, but this is the normal thing for two lines to do.